Well, I'd like to introduce you to impulse and momentum. We're going to start with Newton's second law, F equals ma. And A as defined as dv dt. We'll see that we can bring dt over to that side, and we have f dt is equal to m dv. We now have something we can integrate, and we'll integrate both sides. From v on this side, we'll integrate from v1 to v2. So I'll have on this side the integral of f dt, and this will be, masses being a constant, this will be mv2 minus mv1. We'll define the integral of f dt as the impulse, and you may recognize mv as momentum, and this will be the change in momentum from the momentum in position 2 minus momentum in position 1. Okay? Now, we started with a vector equation, F is equal to ma. The force is always aligned with the acceleration. We did not square the velocity like we did in the energy relationship. So it turns out that then these are still vectors. So we have start with a vector equation, we end up with a vector equation, which means that directions matter, and we will have to make sure we keep track of our x and our y directions when we do that. And we'll find that impulse and momentum are good. It's a good technique, and it's a good shortcut when force and time and velocity are involved in our problems, as opposed to energy, which is a scalar, and we found that energy was useful for force, speed, and distance problems. Okay, so we'll get used to differentiating between what's a good impulse problem, impulse momentum problem, and what would be a good energy problem. All right, since these forces are vectors and the equation is a vector, we'll need to evaluate all three directions, x, y, and z. So here's our equation. Our general equation will be, we'll start with our initial momentum, and we'll add impulse. Impulse could be positive or negative. It could be subtracting or adding to our momentum, and they'll end up with a momentum. We'll have to have the same, and we'll do this in the x direction, and we'll also do the same in the y and the z direction. All right, so energy. In energy, we were able to, if you want to call it, ignore gravity forces. We didn't really ignore them. What we did was we considered all gravity forces and work due to gravity as part of our potential energy. In momentum, we can't do that. We have to consider every force in the problem, and all forces will create an impulse being the force times the time. So all applied forces, friction, and gravity will all be included. All forces will need to be considered even if they don't do work. And what kind of a force would do no work? In general, force moves through a distance and it causes work in that way. In impulse and momentum, sometimes the distances are very small, and that the impulse happens so quickly that the distance might be negligible or maybe not measurable very easily. So in that case, we may have some forces that don't do work, but certainly there could be a very high force that could act through a very small time, and that it will still have a measurable and very significant impulse. So we have to consider all forces even if they don't do work. All right, next thing to note is that if we have a force versus time graph, that the integral area under the curve is the integral of f dt, and that is the impulse. So we may find that we can integrate some curves and find out the impulse that way. All right, and a couple of other things is that sometimes we'll have heavy objects interacting with lightweight objects, and we may find that the heavy object, the impulse caused by the heavy object or acting on the heavy object may again totally outweigh or totally overwhelm the impulse of the lightweight object, and we may find that we can ignore some pieces of the impulse, especially on the lightweight object. Next thing is that impulse has to produce movement. In other words, it has to have some change in momentum in order to be effective. So you can push against the wall for 10 minutes, but if there is no movement, you actually haven't had any change in momentum. All right, and lastly, sometimes there will be systems of particles with a center of gravity. So a system of particles could be two objects, or it could be more. But if all of the forces acting on our system are external to the system, basically those forces will change the momentum of the center of gravity of the system. So the center of gravity of the system follows the same rules as for a single particle. So we'll need to try to keep track of whether forces are internal or external to our system. Okay, so here's just a very simple illustration of momentum and how it relates to F equals ma. But let's say we got a vehicle here that's starting at rest and it weighs 1,500 kilograms. We're going to say the driving force from the tires is 4,000 newtons and it acts through a period of 10 seconds. We're looking for the velocity at the end of that. So let's start with our equation. mv, or momentum, plus the integral of f dt is our impulse and equals our ending momentum. In this case, the beginning momentum was 0. The integral of f dt, if f is a constant, then it's just force times time. Many times the force will be constant, in which case we can just say force times time is equal to our new mv. So force was 4,000, it worked through 10 seconds, and our mass was 1,500, so I can find our velocity was 26.67 meters per second at the end of that. And how does that relate to F equals ma? Well, since everything was derived from F equals ma, we'd expect that we might get consistent results. So let's sum the forces in the x direction and find out what and that's mass times acceleration, and find out what we get. So we're going to find positive direction is this way, the forces were going in that direction. So we're going to say positive 4,000 is equal to 1,500, that's my mass, 1,500 kilograms. Find out my acceleration was 2.667. And then I can plug it into my constant acceleration equations. Velocity is equal to v sub 0 plus acceleration times time. That's a time. And we got v, our new v, is equal to 0 plus our acceleration times 10 seconds. And we get, again, velocity is equal to 26.67. So again, consistent as we'd expect. Maybe we're looking for distance. Again, you don't see distance in our momentum equations. We got mass, velocity, and forces, but no distance. So if we want to look at distance, we have to look at energy or back to F equals ma. So here, let's look at our energy equation. T1 plus V1 plus U naught is equal to T2 plus V2. And if we start from rest, we have an initial kinetic energy of 0. If we are traveling on a flat surface and there are no springs involved, then V2 is equal to V1, so those are both ignored. So what we can say is that U naught is the pushing force of 4,000 acts through a distance S is equal to our change in kinetic energy of 1/2 mv squared. So I just plug 4,000 S 1/2 m is my 1,500. My velocity at the end of that was 26.67, and I can find that the distance it moves in that 10 seconds is 133.3 meters. And that's with energy, but let's check with our F equals ma. And we have two equations we can use to find distance using constant acceleration equations. S is equal to S sub 0 plus V sub 0 t plus 1/2 at squared. Again, we have 0, our beginning position is 0, beginning velocity is 0, so S is equal to 1/2 at squared, and we can find, plugging a into there and t of time of 10 seconds, we can find the distances there. Or we can use our v squared is equal to v sub 0 squared plus 2as equation, plugging those things in, and we get s is equal to 133. So again, all the relationships should work properly, and you can use F equals ma to solve virtually all problems that we're going to consider. But energy is a good shortcut when special conditions are there, and obviously momentum is a good shortcut for if you're talking about only force, velocity, and time. All right, how about this one? This one has a velocity, the force that varies as a function of time. So what we've got here is a log. It's being pulled by this winch here. It's got a motor with a pulley, and so we're going to crank up this motor and we're going to pull this log in this direction. You can see the tension in the wire or the rope follows this little function. So it tops out at 1,800 newtons, but it takes 3 seconds to get up there following this curve of 200 t squared. All right, and the question here is, well, let's look at the details. The mass is 500 kilograms, mass of the log, rests on the ground, coefficient of static friction is 0.5 and kinetic friction is 0.4. Delivers a towing force, and we want to find the speed of the log when t is equal to 5 seconds. All right, t of the speed of the log, so the log's going to go in this direction, and we want to find out when t is equal to 5 seconds. So if we look at the tension graph, we can see that it follows this curve until 3 seconds, and then between 3 and 5 seconds, it tops out at 1,800 newtons. So we have a two-stage problem, and we've done two-stage problems in F equals ma. The powerful thing about momentum is sometimes we can do two-stage problems like this in one equation, and that's really kind of nice. All right, but first of all, we notice that if tension starts at 0 down here, it doesn't start moving right away. So someplace up on this graph, it starts to move, we hope, or we expect. And so let's find out where on the graph that it starts to move. Well, a statics analysis of this will give us something we need to know. We've got two tensions through this pulley, so I'll put 2T over here. I've got an mg coming down, I got a normal force and a force of friction slowing it down. So what I need to know is that 2T has to be greater than the force of friction in order for it to move. So I've got T is equal to 200T squared, so I've got 2T, or 2 times 200T squared, has to be greater than the force of friction of mu mg, or when 2T equals mu mg, that's when it starts to move. And so I can solve this for T. 200T squared is equal to 0.5, m is 509.81, should be 9.81 there, and I can solve this for T to say that it starts moving at 2.476 seconds, which is kind of out in here someplace. All right, now that it starts to move, we have a dynamics problem. So now let's look at our dynamics situation. We can use momentum to try to find out how fast it moves at the end of 5 seconds. But the nice thing again is we can do this all in one step. So let's start out with our momentum equation. mv1, which is going to be 0, starts with 0 momentum. The sum of the forces times time, or sum of the integral of f dt, is equal to our ending momentum. Now so again, it starts at beginning momentum is equal to 0. What are all of our impulses? Well, we've got this impulse. Now, it actually starts to move after 476 seconds. So it's got this piece of impulse that we can count on, and this piece of impulse. So we have to consider them separately, and I can integrate I can integrate them through both of those time periods. So let's integrate the first one. I'm going to say that I have a pulling force of 200T squared dt. Integrate that from 2.476 to 3 seconds. So that goes from here to here. Then I've also got 2 T's going from 1800 from 3 to 5 seconds. So that's what this one is, 1800 dt from 3 to 5 seconds. I got 2 T's there. Now the friction force operates throughout the entire time frame. In other words, as soon as it starts moving from here to here, I've got friction slowing it down. So that's going to be our kinetic coefficient of friction. So it'd be mu mg, and the difference of the time, or times the time, is going to be 5 minus 2.476 seconds. Integrating these things is again pretty easy. 200t cubed over 3, and I got 2 of those evaluated by that, or 2.483. Then I got, this is my the 1800, which operates between 3 and 5, and then here's my friction force, and that's equal to my mass times my ending velocity. Solving that for velocity, I get 7.628 meters per second. So again, a very powerful tool to put multiple things that happen into our problem. Again, a nice thing about momentum and energy is that you don't really care so much about what happens in the middle. You're not looking for acceleration or even mid problem velocities or anything like that. You have a beginning condition and an ending condition, and you don't really care so much what happens in between.